All right, hello. It is so exciting to be here this morning. I'm going to try to keep the energy up from Stephanie and Maddie, but they set the bar really high. It is so exciting to be here. Hello to everyone on the live stream. So as Maddie said, my name is Niyogi. I'm a rising senior at Johns Hopkins University, where I study applied math, statistics, and economics. As you probably picked up on, those are not very earth science related fields. So while I will be presenting a comparative analysis of tropospheric nitrogen dioxide, more than that, I really want to take you along with me as I highlight the stuff that I learned and experienced throughout this internship. Before I forget though, the top left-hand corner has a QR code for my supplementary information slides, which contains extra plots and explanations. But more than that, also has access to my GitHub repository with the code. All right. So I'd like to begin by going over the SARP flights. So as Stephanie mentioned, SARP is short for the Student Airborne Research Project. And this year, its West Coast campaign had 8 B-200 flights and 5 P-3B flights. Now, all these flights took different routes for various data collection purposes, and both planes had a unique suite of instruments, some of which were remaining from the ARC-6 campaign in Greenland. So, as Stephanie mentioned, we received a few lectures before we actually got on the planes so that we would understand what processes we were seeing around us and also what the measurements meant. So one term that came up a lot was NOx emissions and NOx. And I quickly learned that NOx is actually an umbrella term that's used to describe nitrogen monoxide, NO, and nitrogen dioxide, NO2. Now, NO2 in particular is important because when it reacts with UV rays from the sun or with volatile organic compounds in the air, it can result in ozone formation, aerosols such as particulate matter, and ultimately can lead to a lot of health effects in communities around us. NO2 itself is relevant to study due to its anthropogenic human sources. So the EPA cites that 50% of tropospheric NO2 is due to cars and transportation, 20% is from electric power plants, and then 30% from miscellaneous other sources. With NO2 playing such a large role in our lives, we have many ways of monitoring it. One of those ways is through ground stations. These are well calibrated, but we often find that they can be limited in terms of their individual space, coverage, and then scale. So if we wanted to issue, say, a health alert, we can't confidently do that solely with ground station information. That's where satellites come into play. Satellites are useful tools due to their large coverage, their predictable and routine path, and their repeated measurements. And that brings me to today's main player, the TEMPO satellite. TEMPO is actually short for Tropospheric Emissions Monitoring of Pollution. It launched in August 2023, and its data became available for use in May 2024, so just a few months ago. It is the first ever space-based instrument to monitor air pollutants hourly across the North American continent during the daytime. And in addition to providing hourly measurements, it does it with an insane grid coverage of 2 by 4.5 kilometers. When I heard all this during the first few weeks, I knew that this is a satellite I wanted to work with. And as such, that brings me to my research question that I've spent the past few weeks studying. How do TEMPO-derived values compare to the vertical concentrations of various gases, specifically nitrogen dioxide? Well, this is kind of a lofty goal. So the first thing I did is I broke it down into 3 more tangible goals. My first goal was to calculate the total amount of nitrogen dioxide in the troposphere in an atmospheric column from airplane measurements. My second goal was to get a single TEMPO value for the time and location of each of those columns. Then my third goal would be to use the output from goal 1 and goal 2 to create data points for comparative statistics. So the first thing I had to check is if nitrogen dioxide was even recorded on these flights. Well, the CANOE instrument, Compact Airborne NO2 Experiment, was on the B-200 and was equipped for the ARC-6 mission. It used laser-induced fluorescence spectrometry to record NO2 concentrations in the air, and this is the instrument that I used to get my data. So, since the CANOE instrument was on the B-200, I went into all of the 8 B-200 flights that we flew and saw where they performed spirals. For those unaware, a spiral is essentially when the plane is in one relative latitude and longitude, it quickly ascends in altitude and then descends in altitude, collecting measurements. I found of the 8 flights, 6 of them performed spirals, meaning I potentially had 6 spirals to compare with tempo data. From there, it was a matter of processing the spiral airplane data. What I ended up doing was a 3-step process where I created concentration averages based on altitude, converted from parts per trillion by volume, which is what the canoe instrument records in, and converted it to molecules per centimeter squared, which is what tempo's measurements are in. From there, I summed for a total nitrogen dioxide concentration. That was a lot, so I have a little visualization here. As you can see on the right, I have an average vertical profile during the June 29th spiral. And so what I did is I essentially partitioned it, and these are my altitude averages, by 500 feet, found the area of each of these rectangles, and then summed all of them to get my total column concentration. With that, goal 1 was done. My second goal was to produce a tempo value for each spiral, but once I got my hands on the data, I really wanted to plot it first. There were 2 things I kept in mind. For plotting purposes, it was easiest to average the latitude and longitude that was traversed by the plane, and then say that the spiral took place exactly at that average. The second thing I wanted to ensure was that if the spiral took place during 20 UTC, it also ended in 20 UTC, so that I was comparing spiral data to exactly 1 tempo measurement. So with that, I found that tempo is accessible through Earth Data Search's platform in NetCDF form. However, tempo is such a revolutionary satellite that the EPA has already integrated it into its PureSig Python package. And that's ultimately what I used to make the following plots. So on the right, you'll see my little tempo plot for the June 29th spiral again. The black marker is where the spiral is said to have taken place, and that's also how I produced a tempo value to compare to the spirals. With that, goal number 2 was done. I was able to do this for all 6 spirals that took place on the V200, meaning I had 6 data points that I could use to compute some comparative statistics. So the first thing I wanted to do, now that I had these 6 points, was understand the data. I wanted to understand if the tempo output and the flight output was similar. My hypothesis was that the tempo satellite data and the flight collected data for tropospheric nitrogen dioxide are similar at a 0.05 significance value. I computed a few tests, some of which assume independence between the sets, some which don't, some which assume a normal distribution, some which don't, and all of them led us to believe that we have reasonable evidence to conclude that the tempo satellite data and the flight collected data for tropospheric nitrogen dioxide are similar, even if tempo reports lower values. Now, the next thing I wanted to understand is how similar is this data? So there are a lot of numbers on the screen, trust I understand, but I'm going to highlight some of the values I want you to pay attention to. The first is the mean bias, which is the average of all the biases and tempo data versus flight measurements. Here we see that tempo tends to record lower values on average, and my idea is that it's likely due to the hourly intervals of data that I worked with. The next statistic I would like to point out is the skew. The skew shows us if tempo overpredicts or underpredicts in comparison to flight data. Here we see tempo slightly underpredicts, so a little more support for that. But that is likely because of either better ground level measurements by tempo or due to the hourly intervals once again. All right, so that was a lot. So just some final thoughts on a slide for us to walk through together. We do see some agreements between tempo satellite values and the flight measurements. Now, as for why there might have been disagreement, I do not have time to look too much into that, but I do have a few ideas that I would love to investigate in the future. The first is that I compared hourly tempo data against super specific time intervals. I think it would be very interesting to see what would happen if I was looking at a longer time frame. The second, as I mentioned, is that the spiral data was heavily averaged. So the cumulative concentration was estimated and not exactly measured in the plane. Tempo is a satellite, so it can record ground level values where the plane could not reach. So that may affect the values as well. My third idea is that flight spirals may have crossed into multiple tempo grid cells. As you recall, I averaged the latitude and longitude, assuming that the flight was solely contained in one gridded cell. It's very likely, especially since tempo is so high resolution, that the plane spiral crossed into multiple grid cells, meaning that one value cannot fully encapsulate what the flight measured. All in all, tempo data was lower than flight data, but we still found them to be statistically similar. With that being said, I would like to thank you all for your time. I would especially like to acknowledge all these people on the slide for their help. My faculty mentors, Dr. Andreas Beiersdorf and Dr. Anne-Marie Carlson. My faculty mentor, Maddie Landy. Dr. Disha Sardana for all her help with my code. The Aerosols group for their help. Dr. Jason St. Clair, who is the PI for the canoe instrument. The NASA team that allowed me to be here today. Dr. Barry Leffer for helping me understand how tempo works. And then all of you for your time, and everyone on the live stream, hi Mom, hi Dad, for your support today. Thank you so much. I'll take any questions if there are any about my experience in the program, the project, anything. Yes?
I have a question, sorry. If you could go back a couple slides, it's the tempo, the tempo slide versus your prediction. That one, thank you.
Okay.
So, I mean, from back here, they look like they agree pretty well, the tempo's lower, but maybe I'm misunderstanding. It seems like the average or the median line, I'm not sure which it is, with tempo is below 2, and the average for those is like 6.
Yeah.
So, I'm not big on statistics, but I mean, to me, that, saying that's slightly lower seems, I mean, unless maybe we were expecting like a factor of 10 difference, I don't know.
Yeah, so that's actually a really good point you bring up. So when I first did the calculations, I was looking at, I think, what was it, 10 to the third magnitude difference. And so when I first got that, and then when I adjusted things for temperature and pressure, altitudes, things like that, then I was finding something like this.
Okay.
So relative to the first result, I thought it was much better.
It is, yes. Okay, thank you.
Yeah. Any other questions? Yes.
Did you look at all at scatter plots? Like, is it a linear relationship or does it go non-linear at all?
Yeah, I did actually look at the scatter plot. There is a pretty nice linear fit. I
Cool.
believe the R factor, or the R coefficient is negative 0.62, about an R squared of 0.38.
Cool.
Yes, Ella?
First of all, I think you did a wonderful job.
Oh, thank you.
It was a really beautiful presentation. I'm just wondering if, because the planes don't start at 0 altitude, is that a difference between the satellite, which might get down farther?
That's a great question. Thank you for asking. So there were a couple of assumptions that I had to make. So let me go to that slide real quick. All right. So it's exactly as you said. The flight spiral was probably between 10,000 feet and maybe 2,000 feet at lowest. Now, we made the assumption that anything above 10,000 feet, since I was looking at tropospheric levels, was negligible. However, there is a large concentration below where the plane could measure. So what we ended up doing was assuming that, all right, if this is the level that was recorded at 2,000 feet, let's assume that's the level for all feet below, from the surface to where the plane was. And then we ended up doing that as like a constant. So it would end up being like a larger rectangle for this, summed, plus all of the plane measurements. Of course, thank you. Good.
Any other questions for Maya? No? Well, thank you.
I have a question. I saw a table. Don just raised a question. I saw one case, tempo is much higher than SARP, and another case, the SARP is much higher than tempo. If you go back to the table.
This one?
Okay. Can you see on the second row, the tempo is 1.6 and SARP is almost 9, right?
Yeah.
And then you see the last row, tempo is 7.5 and SARP is about 1. Do you see any profile difference, I mean vertical distribution difference in O2 wave from SARP? Thank you.
Thank you for your question.
That's Gal, by the way, you'll hear him a lot. Yeah.
You saved my life.
I do have the vertical profiles, but off the top of my head, I can't come up with any differences that I can think of right now. I would love to look into that more and get back to you. Anyone else from the live stream? Yes, Stephanie.
We have an online question. Was there any wind direction or event, smoke transport and boundary layer based bias notable?
Ooh, that's a really good question. That is not something I looked into, but I would love to look into that and see. I was considering the high split model for a certain period of time, but I ran out of time to factor that into my analyses.
Just on that note, we also recorded wind direction, number of meteorological data on the V200 that if you ever wanted to integrate into this data set.
That'd be great. Thanks,
Okay.
Katie. Yeah, thank you.
Any other questions from the audience? Yes.
I just want to make a comment, like those differences look big, but that's the number of molecules per square centimeter. It's not even a mole, right, over a whole entire element.
Yes,
A great presentation. I just wanted to say that the V200 also did some spirals over Baltimore, about 8 or 10. The week before it came out to California, and so you could double your data set by looking at Los Angeles and Baltimore in the future when you have time.
That's great. Yeah, no, I genuinely would love to do that. Thank you.
All right.